So let me begin by taking a minute to thank the organizers of this nearly carbon-neutral geometric topology conference. First of all, for bringing this wonderful group of people from so many areas together. And second, for giving me the chance to present my work here in this new format, at least for me. So this will be the first part of a two-part talk, and the idea is that in this part I'll try to cover very broadly what the motivation behind the topic of this talk is and what the main techniques are. And on the second part, we will go into more details on how to carry out these techniques properly. Yeah. So let me now begin with the actual talk. So what I want to talk about today is about certain counting problems for simple closed multi-geodesics on hyperbolic surfaces. And the idea of these counting problems is that they will be concerned with the lengths of individual components of the multi-geodesic. And I'll explain throughout the talk what I mean specifically by this. So here's the outline of the things that I want to mention today. So I want to begin with a quick review of Mirzahani's work on the subject, and this will basically mean to talk about counting problems for simple closed multi-geodesics on hyperbolic surfaces, but where the quantity we want to count with respect to is the total length, and I'll explain what that means. Then I want to move on to discuss a conjecture of Scott Wolpert, where the object of interest is again simple closed multi-geodesics, but now we want to count not with respect to their total length, but actually the lengths of individual components. And I'm gonna explain through the talk what the main difference between these counting problems is and why new ideas need to be introduced. And finally, I want to discuss a proof which is inspired by ideas of Margulis and which is inspired by a very general set of ideas coming from homogeneous dynamics based on equidistribution phenomena for what we call expanding horrorballs. In the setting of this problem, it's going to be expanding horrorballs on moduli spaces of hyperbolic surfaces. Yeah. So let me begin by introducing one of the central concepts throughout the rest of this talk, and that's the idea of the topological type of an ordered simple closed multicurve. So the setting is going to be the following. I'm going to consider a closed, connected, oriented surface, S. Whenever I say surface, I'll mean all of those adjectives at the same time. And on that surface, an ordered simple closed multicurve is just a tuple of pairwise disjoint, pairwise non-isotopic simple closed curves. Yep. And if I have any two such ordered simple closed multicurves on two homeomorphic surfaces, which here we call S1 and S2, then we're going to say that they have the same topological type if one can find a homeomorphism from one surface to the other, which takes one of the ordered multicurves to the other ordered multicurve, respecting the order that's implicit in the tuple. Yeah. So that's sort of the formal definition, but sort of at a very broad level, the topological type of a multicurve should capture just how it looks on a surface up to homeomorphism and isotopy. So let's see some pictures over here. So here are some examples of different situations that can happen. So in this first case, these two multicurves have the same topological type because they both do not separate a genus 2 surface. In contrast, in the second case, we have two multicurves that have different topological type because one separates a genus 2 surface. Sorry, this one separates a genus 2 surface and this one doesn't separate. In the third case, we have two separating curves in genus 4 surfaces which do not have the same type because they do not cut the surface into pieces with the same topology. And in the last example, we have two curves that do not have the same topological type, but even though they're cutting the surface into the same pieces, the curve over here doesn't have separating, the multicurve here doesn't have separating components, while you can see that this multicurve has this separating component. Yeah. So topological type should basically tell us how our curves look on the surface up to homeomorphism, and they usually, the point of these examples is that they, that notion tends to encode more information than one might think in first instance. Yeah. So okay, so that's the main concept that we're gonna mention throughout the talk. And now let me introduce what Mirzahani's counting problem is. So here's the setting. We're going to look at X, which is going to be a hyperbolic surface of some genus, G, bigger than or equal to 2. So hyperbolic in this setting just means having a metric of constant curvature minus 1. On that hyperbolic surface, we're going to have a ordered simple closed multicurve, which we're going to denote by gamma. And together with that information, we're also going to have a vector A, which is going to be a vector of weights on the components of gamma. Yep. And for every number L, we're going to consider the following counting function. Here, T stands for total length. So what we're going to count is the number of ordered simple closed multi-geodesics. And when I say multi-geodesic, I just mean multicurve, all of whose components are geodesics. So we're going to count the number of ordered simple closed multi-geodesics alpha on X, which have the same topological type as gamma, the multicurve that we fixed beforehand, and such that the length of the multi-geodesic satisfies the following constraint. If I add the length of the components and I weight them by the weights A, then that's going to be bounded by L. Yeah, so we should interpret this as as total hyperbolic length with weights A. And given this counting function, the question that we want to consider is how does this quantity grow as we take the parameter L to infinity? Yeah. And the answer to this question was given by Mirzahani in her thesis. So what Mariam proved is that this quantity that we were trying to count grows asymptotically like L to the 6g minus 6, and moreover, we know that the leading coefficient of this asymptotic can be described in the following way. It has a factor which depends on the weighted multicurve, so that's A times gamma, and we usually call it the frequency of that weighted multicurve. It has a factor which depends on the hyperbolic structure, and we usually call that the Mirzahani function, and then there's also some normalization constant which depends only on the genus. Yeah, and I'm not gonna give a precise definition of what the frequency is and what the Mirzahani function is, but at least first let me say that I think that one should remember about the Mirzahani function is that if the surface develops very short curves, simple closed curves, then the Mirzahani function is going to blow up. So in some sense, it's measuring the shortness of GD6 on the surface. And there are two other features that I want to highlight about this theorem. One is that the right-hand side here, this leading coefficient sort of splits as a product, which depends on one factor depending only on the weighted multicurve, and another factor depending only on the hyperbolic structure, and that's very useful for several applications. Which I'm not going to present in this talk, but I just wanted to mention that because it's important. And the second thing, which is also important, is that even though I'm not giving you a definition of what this frequency is, I just want to say that it is computable in the sense that you can write an algorithm, or if you're patient enough, you can compute it by hand, which gives you the value of this rational number. Yeah. And I guess I should say that this, I didn't mention it this way before, but this number is rational as long as the weights are rational. Yeah. And yeah, so that's sort of Mirzahani's original problem. And let me now introduce a conjecture of Scott Wolpert, which is going to be motivated by the following question. What happens when we consider countings of ordered simple closed multi-geodesics where we want to keep track of the lengths of individual components of our multi-geodesics? Yeah. And so let me make this more precise. So we're going to consider a hyperbolic surface X of genus G bigger than or equal to 2 with all the hypotheses that I've assumed elsewhere, in particular closed. Gamma is going to be an ordered simple closed multicurve on this surface. as before, and now I'm going to consider a set of parameters b, which are not going to be weights, but I'm actually going to call scaling parameters to be a bit more precise. And the counting problem that we're going to consider is that for every number L, we're going to count, and here C stands for components. We're going to count the number of ordered simple closed multi-geodesics on my surface of the topological type given by gamma, and satisfying the following constraint on the length. The length of each component should be bounded by L times the scaling parameter corresponding to that component. Yeah. So let me leave the definition there for a second, but let me also, 1 second, present an example that might make this a bit more intuitive. So say that we let the vector b be just once on all of its entries. Then this counting that we're going to see is going to count the number of ordered simple closed multicurves on my surface of the prescribed topological type, and having the restriction on the length being such that the maximum of the length of the components is bounded by L. Yep. And so a way to differentiate these two problems in our head is that we should think about this second problem as some sort of L infinity counting problem. And we should think about the original problem, which is here, as some sort of L1 counting problem. After weighting the components, this is sort of like an L1 norm, and what we have here is some sort of L infinity norm, or even here. Yeah. And so the question, just as before, is to understand how does this quantity grow as we take the parameter L to infinity. And so that's the question that we want to think about, and let me tell you the answer. So the following theorem was at least proved by 3 groups of people, and the presentation in each case is different, and the motivations are different, and you can move from one statement to another with enough work, but I just want to present the version that I proved. So the authors are Liu, who's a student of Anton Sorich, Vivek Arlanson, Juan Soto, and then myself. And the version that you see here is the one that I present in my work. So the statement is that this quantity that we're concerned with grows like L to the 60 minus 6, and so goes to infinity, and is asymptotic to L to the 60 minus 6, and the leading coefficient admits the following description. Again, it has this Mirzakhani function factor divided by this normalization, but now instead of having this frequency, what we see is an integral, and sorry about that. So we see an integral, and this integral is the integral of some polynomial, which here's a description that you can read on the screen. And we integrate that polynomial over the box defined by the scaling parameters. Yeah, and just as in the previous case with the frequency, the feature that I want to highlight is that this polynomial is computable in the sense that one can write an algorithm which tells you the polynomial, but to say maybe a bit more, this polynomial corresponds to the top degree terms that show up in Mirzakhani's integration formula, if you've ever seen that, but I'm not going to use anything of that explicitly in this talk. Just wanted to give some context there. And maybe let me, if I'm not going to give a definition, at least let me try to convince you with some pictures that these are computable. So here are some examples in the genus 2 case. So here you can see some polynomials that you can compute. These are all possible topological types of multi-curves on a genus 2 surface. And maybe the other feature that I want to highlight is that when you have a pair of fancy composition, the polynomial is always a product of the xi factors by some constant, which might take you some time to compute, but it always has that structure. Yeah. So those are some examples to convince you that everything is computable. So now let me say a few words about Mariam's proof. One, because it's a very good starting point, and second, because I want to sort of explain what the difference between these two counting problems is and why do we need new methods for our work. So I want to talk about Mariam's original proof in a simpler context. So I'm going to consider a classic lattice counting problem. I'm going to take a unimodular lattice here called lambda, and I'm going to count the number of primitive points on that lattice that lie inside a ball of radius r. Yeah, and I want to know how that grows as r goes to infinity. So let me give you some way to prove this theorem, which might not be the usual one, but it's going to be, for motivation, important. So I want to assume first the fact that SO2Z acts ergodically on R2, and you can prove this using the fact that the horocyclo flow on the space of unimodular lattices is ergodic. And the idea is that assuming this fact and using Siegel's famous integration formulas, you can actually show that the following measure convergence holds. So I'm going to put a delta mass on every primitive integer point, like here. And then I'm going to scale that point by 1 over r. And I'm going to scale that whole measure by 1 over r squared. And then what this is going to tell you is that this measure is going to converge to a multiple of Lebesgue measure. Yeah, so maybe to make this more clear, the idea here is that if I, instead of putting delta masses at primitive integer points, if I put them at all integer points, what I would get here is the definition of Lebesgue measure as a rescaled counting measure of integer points. Yeah, so imagine putting delta masses at all integer points rescaled in this way, then this would converge to a Lebesgue measure. If you do it for a finite index subgroup of the integers, then you wouldn't get Lebesgue measure, but you would get Lebesgue measure multiplied by 1 over the index of that subgroup. And what this result is saying is that, okay, so Z2 prime, so the primitive integer points are not a subgroup, but they are a a SO2Z orbit. So it's the SO2Z orbit of the vector 1, 0. And so what this theorem is saying is that ergodicity ensures that this SO2Z orbit is distributed well enough so that when I do the same rescaling process, even though it's not a finite index subgroup, the ergodicity ensures that the points are well distributed so that the rescaling process still gives me a multiple of Lebesgue measure, and in this case you can compute explicitly what the multiple is. Yeah. So that's sort of what the content of this statement is. And now once you have this statement here, to get information about the counting problem that we cared about, now we just evaluate on the right set. So when you want to go from weak convergence of measures to convergence after evaluating on sets, you need to apply Portman-Toe's theorem, and that requires the set that you're evaluating on to be nice. And sort of, for instance, if it's the sublevel set of a function, it should be continuous, and that's what's going to happen here. And I'll just leave it as an exercise for you to evaluate both sides and notice that you recover this exact expression over here. Yep, and that would give us an answer to the counting problem that we cared about. So then if that's the case for counting primitive lattice points, then Mirza's approach is basically a similar thing, just following the following dictionary. And for this part of the talk, I'm not going to define any of these terms, but I just want to show you that there's like an explicit correspondence of objects in one proof and the other. So the SO2Z action becomes the action of the mapping class group, which, if you're interested in, is going to show up in the second part of this talk. R2 is going to become the space of measured geodesic laminations, sort of a space that interpolates through all multi-curves. The primitive integer points are going to become a mapping class group orbit of the curve that we care about, the weighted multi-curve that we care about. The Lebesgue measure is going to become what we call the Thurston measure on measured geodesic laminations. And instead of evaluating on the sets that we evaluated before, we evaluate on the set of all measured geodesic laminations whose length on the hyperbolic structure that we care about is bounded by 1. Yeah. And what I claim is that if you follow this dictionary and if we know that what these things mean, then you will be able to get a proof of Mariam's original theorem. But I'm omitting something that's very important here, and which is probably one of the most outstanding aspects of her work, is that before I mentioned that you're going to need some integration formula, in this case Siegel's integration formula. What you need in this case to finish the proof is Mariam's analog of Siegel integration formulas for countings of simple closed multicurves. Yeah, but I'm not going to mention exactly what that is, but that's a big part of the content of her proof. Yeah, and now maybe let me say why does this strategy does not apply in our case, and let me give you two reasons, although there are several more. So one reason is that when we did the last step in this previous proof, when we evaluate on a set, we need to apply Portman-Toe's theorem, and that in particular requires the set that we are evaluating on to be nice. In particular, like here, come from a continuous function, like a sublevel set of a continuous function. And the problem is that the notion that we want to count with respect to is this length of individual components, and there's sort of no way to extend that continuously from the space of multi-curves to this completion, which I've called the space of measured geodesic laminations. So it will certainly not be something like evaluating on a better set, on a more convenient set. And a second sort of maybe a bit more conceptual idea is that Mariam is counting with respect to these L1 simplices, and we want to count with respect to these L infinity boxes. And one can see, just measure theoretically, that these sets do not generate the boxes of this form. So you should not expect to be able to get information about this just from knowing what happens on simplices. Yeah. So that's just to give some idea of how this why we need new ideas. So let me kind of mention a brief sketch of what the new ideas entail. So we were talking about this counting problem for primitive integer points inside a ball of radius r. And one way of tackling this problem is how I mentioned before, but another way, which is probably more familiar in the world of homogeneous dynamics, is that instead of studying these counting problems, you can reduce them to statements about equidistribution of expanding horoballs in the case of counting primitive points, horoballs on the space of unimodular lattices. And then you can study that equidistribution result using the dynamics of some flow. Here I'm citing horocyclic flow, but in the case of unimodular lattices, you can also use geodesic flow. Yeah. So let me briefly sketch what the upshot of this idea is and what the content is in the setting of counting primitive lattice points. So I give you a lattice lambda, and I want you to count the primitive points that land in a ball of radius r. And I claim that that's might be hard. Yeah, it might be hard to do it just for one particular lattice. So instead of tackling that, let's just average the counting problem over lattices nearby my original lattice in this space of unimodular lattices. And you say, oh, big deal, you just average the counting problem. Here, where I mean near, I'm thinking about lattices that are nearby, so that when I take the average counting problem looks very similar to the original one. And what's the advantage of having averaged? The idea is that once you average, there's standard unfolding techniques to unfold such averages over some suitable cover, and then your original problem reduces to a problem about equidistribution of certain families, which we call expanding families of horoballs, and you want on the space of unimodular lattices in this case, and now you've reduced your problem to a statement about equidistribution of certain sets, and we've gained a lot here because now this is an equidistribution question, and that clearly lands in the domain of dynamics and ergodic theory. And in this case, we can use the dynamics of the horocyclic flow, in particular certain ergodicity properties and non-divergence properties, to show that these families of expanding horoballs equidistribute with respect to the Haar measure on the space of unimodular lattices. Yeah, so that's sort of an idea of how this sort of mindset works. And what I want to say is that in our setting, we want to apply the same strategy, but we want to follow a dictionary, just as I mentioned in Mariam's case. Instead of counting primitive integer points in a ball of radius r, we're going to count ordered simple closed multi-geodesics on my surface, which have topological type gamma, the topological type I prescribe, and which satisfy the constraint on the lengths that I wanted. Instead of looking at the space of unimodular lattices, I'm going to look at the moduli space of genus G hyperbolic surfaces. Instead of looking at expanding horoballs, I'm going to look at the classical expanding horoballs. I'm going to look at some appropriately defined horoballs in this setting, and that's going to be explained in the second part of this talk. Instead of considering horocyclic flow, I'm going to consider earthquake flow, and I'll also mention what that is in the second part of this talk. And things won't equidistribute to sort of the natural counterpart of Haar measure here, which is Weil-Pearson measure on moduli space, but they'll equidistribute with respect to some density, which is the Mirzaani function, times the Weil-Pearson measure. Yeah, so that's sort of the global idea of what is going on. And maybe before I end this first part, let me just make 3 more remarks. everything that I said will work perfectly for surfaces with punctures. It's not an issue. I'm just assuming closeness here to make things easier to explain. There's a more precise version of the counting that I present, which would correspond to bisector countings in the classical case, where you keep track of more information, sort of the class of the multi-curves on projective measured laminations, but I may not mention anything more than that. And the last thing that I wanted to mention is that one can also consider countings of filling closed multi-geodesics, where you keep track of lengths of individual components, and you can also solve that problem, but using completely different techniques, and also inspired by later work of Mirzahani. So yeah, so this is going to be sort of the end of the first part of the talk, and in the second part of the talk I want to focus on describing what these expanding horribles are in our setting, and how do we show they equidistribute, because that's sort of the problem we reduce to through the techniques I presented here. Yeah, so I'm gonna stop there.